Hi, good morning, and welcome to the ZP Developer Zone. So every Thursday at 8 a.m. London time, we do a ZP Developer Zone webinar where we try to summarize or discuss some of the questions that have come in from sensor developers and biosensor developers or users from around the globe. So every week we quickly show this screen. We say, look, we have the ZP Academy. So probably today, if you're new to sensors, we have the ZP Academy, and it's definitely worth Googling the ZP Academy. And there's a couple of free courses on the Academy regarding biosensors and regarding techniques like amperometry, potentiometry. So you should definitely take a look at that. We have the webinars we do every Thursday, and we have collaborations, we have jobs, and we have the Developer Zone website itself. And then we also have workshops. Yes, it's probably worth mentioning the workshops. We're going to have a workshop in Norway. I think it's in Q4 this year, and it'll be around biosensors, including CGM, continuous glucose monitoring. So let me go in a little bit now. So we've got 4 questions this week. So if you're one of the questioners, you can sort of jump around in this video in terms of, we're going to first of all deal with pH in bioreactors. Then we're going to discuss monitoring hydrogen peroxide in a flowing stream of water, measuring lactic acid in a fermentation broth, and biosensors for ATP, adenosine triphosphate. So first of all, question number 1. So this is question number 1. It sort of came in various parts during the week, so I'll sort of jump. The first question that came in is that the person wants to measure, they actually want to measure temperature, pH, and probably use it for gas control. You can essentially, a lot of people use, if they're measuring pH, they can use a carbon dioxide stream to control pH. So that's why I think they talk gas control. I'm not discussing temperature here. The reason I'm not discussing temperature is it's so easy. It's not the hard part. Let's say, in some ways, temperature's so easy, sort of pH is just a different beast altogether. Whenever you go from making these condition type sensing, temperature and pressure, to making chemical measurements like pH and dissolved oxygen, now there's a sort of a step change in difficulty. Anyway, let me jump into it. The first question I had was, we want to measure pH, and then the second question was we want to measure it in an Arduino environment. So I will go through and discuss this. First of all, it was nice of them to send me a drawing. The biggest thing I quite like, we've got a couple of questions this week which are very different because they're not people trying to do what we call point of care. They're actually trying to do much more industrial process control. And so they have I imagine this thing is quite large. We're talking, sort of meter scale here. Bioreactor. And into it, they want to put for example, in their first question, it was a pH sensor. So the biggest thing here is actually NRE. NRE is non-recurring engineering charge. Somebody's got to sit down and, essentially do the engineering to make sensors that Zimmer and Peacock have. And so our sensors, I've kind of sketched, our sensors are actually intrinsically quite small. That the whole object is about 7 millimeters by 25 millimeters, and so we're small compared to the application itself. But of course, you've got to sort of figure out the engineering. How do I take this small piece and get it into my in this case bioreactor? And these things are, you can. I'm going to say kludge things together, but to do it nicely, it takes a bit of engineering charge or cost, let's say. So there's an NRE, a non-recurring engineering charge, and that's either something that the company would do or would outsource to a company like Zimmer Peacock. I just want to say hi to Aftab, who's online this morning. Nice to see you, Aftab. So this is definitely something that Zimmer Peacock is interested in doing, which is putting our sensors into process control. So the question comes in and says, I want to measure pH, I want to measure it in a bioreactor, and I want to do an Arduino environment. So one of the biggest challenges is taking our pH sensor and actually getting into that reactor, physically getting it in there and making sure that The points on a sensor that need to be wet are wet, and the points that need to be on the sensor that need to be dry are dry. And it's not trivial. They did expand the question to pH, temperature, dissolved oxygen, and conductivity sensors. So I just want to say, this is, I said question 2 here, this is still question 1. We do have a pH sensor, we do have a dissolved oxygen sensor, and we do have a conductivity sensor. And I have put these links underneath the video. So I just want to say that we do have these various sensors, but I'm only focusing on the pH because that was the first question that came in. And to be honest with you, you have to kind of, you have to tackle the pH first of all before you start getting into the dissolved oxygen, the conductivity sensor. But we do have all 3 of these. And it's a bioreactor, so I can imagine that they want to measure pH because that's obviously good for the microbes that they're growing. Dissolved oxygen, how much oxygen is coming to those microbes, and then the conductivity, is a simple enough sensor to do as well. So we do have a pH sensor, and I'm going to put a link. There's a link here, and I've also put it underneath the link of the video. So there's a particular pH sensor that I'm recommending. It's called the Hypervalue pH sensor. The reason being is when you buy enough volume, it's going to be a very low cost sensor. It will definitely work. I mean, we've been using this sensor for years. Just a sort of, if you do get hold of these sensors, you actually just have to measure the voltage between 2 of the connectors here. This pH sensor is, it's basically a voltage generator, and you have to measure the voltage between these 2 parts here. Now, they did ask the question, how do I measure using an Arduino environment? So the quick answer is, if you look up measuring pH with Arduino, you will find a lot of material out there on it. If you do search on Google measuring pH with Arduino and you put Zimmer and Peacock, you'll find an old article of ours. We wrote it in 2018. I don't currently support this article. We haven't updated it since 2018. But measuring pH with Arduino, I did a Google search recently, and I could still see that people were Googling on this. I think measuring pH with Arduino is the easiest one. Measuring dissolved oxygen with Arduino is tougher and needs a bit of engineering. And measuring conductivity with Arduino, these things can happen. I think there's a lot of pH. There's a lot of dissolved oxygen and conductivity sensors out there that kind of give out a signal that's 4 to 20 milliamps. So you get into this whole palaver, I would say, of having to convert a 4 to 20 milliamp signal into something that you can then read. So at least with the pH, you can just use a ZP pH sensor and measure it with Arduino. We've definitely looked into that ourselves. If you get stuck and you're looking for a low-cost electronic solution for pH, and we do have something, it's only €250, and there's quite a lot of support material on the website. So hopefully, either follow the link here, or I've also put a link underneath the video as well. So the person wants to measure pH, initially it was pH, in a bioreactor in an Arduino environment. So pH sensors are fine, we've got them on the website. Arduino's fine, we've done it ourselves, other people have done it. Your biggest challenge is really making that pH sensor into your reactor. It's the whole fittings part, because you have to get the sensor into the solution, but you don't want the solution to get out of the reactor, and you certainly don't want it to get onto the electronic connectors. So and then if you do get stuck on the electronics, we do have a low-cost OEM solution that's probably worth taking a look at. I haven't discussed dissolved oxygen. I haven't discussed conductivity. I want to see how they get on with pH before they go too far along the dissolved oxygen, the conductivity. Other than to say that we do have those sensors on the website, and you can sort of take a look at those. Now, question number 2. This is a really interesting one. I think this is in some ways simpler than the first one. They're looking for a technology for quantifying hydrogen peroxide in tap water. So there's essentially a sort of plasma generator that treats tap water, and it gives out, it's a 1/2 inch outlet, which is approximately 12.5 millimeters. And they have quite a quite high flow rate, 4 liters per minute, 25 ppm parts per million of hydrogen peroxide. which I've calculated. We do have a calculator on the website for this, by the way. Calculated it's 0.74 millimolar. So 0.74 millimolar hydrogen peroxide is actually quite high. And the reason that's a positive is because it's easy for us to measure. Essentially what's going on, again, I haven't recommended exactly which sensor to use, because in some ways this application is quite harsh. There's quite a lot of hydrogen peroxide generated, so you almost want to try several modes until you actually decided which one to use. When I say several modes, we can run hydrogen peroxide detection in what's called a redox probe mode. We can use a TAS sensor, that's total antioxidative status, or a FRAP sensor, I think that's ferric reducing something power, I think. So there's several ways of measuring hydrogen peroxide. I think all of them will work. You have to try them because you're actually producing quite a lot of hydrogen peroxide, and you'll be doing it for quite a long time. So that means that it's quite corrosive what you're trying to, for the sensor it can be anyway. So we have, I'm absolutely sure it'll work. But what we're expecting this is that you'll have a signal versus time. So your signal in tap water will be, essentially baseline. Then if you turn the machine on, you'll essentially start generating this hydrogen peroxide, at which point the signal will jump up and respond. Now, I've deliberately put some noise on that signal because you've got 4 liters per minute going through a 12.5 millimeter diameter tube. It might be a little bit turbulent in there, so I'm sort of reflecting the fact it might be turbulent, but it's not a big deal. It can be filtered or you can just live with it. At which point then I suspect that when you turn the machine off, the hydrogen peroxide will stop. It'll be cleared out quite quickly, and you will have a sort of low signal. So I don't have a big issue with this application. I think it's quite a straightforward application. I think the concerns are the lifetime of the sensor, and you almost have to have an engineering process where you decide, am I going to have a sensor in here that's for life? But having a sensor in there that's for life, sitting in a approximately 1 millimolar hydrogen peroxide solution, could be a little bit corrosive on the sensor. But it's all about duty cycle. How often is this used for? How long is it used for? I would almost, from the first instance, you almost have to try it, and then the second instance, you have to think, do I treat the sensor as a semi-disposable? Now, I've touched upon this in the bioreactor question, and now I'm touching upon it in this hydrogen peroxide generation question, which is, we do have these sensors, and at Zimmer Peacock, we've spent a lot of time putting them into these aqueous environments, these water environments, and we end up doing a lot of potting. And by potting, I mean, we take the sensor, we leave the sensing end exposed, but we then have to really protect the electrical connection. So essentially this box is almost completely filled with epoxy, because you can imagine, we don't want to stop any ingression of liquid. And when we've done that, then these cables are, are fairly okay. We can just pull these cables out, put them anywhere. Just to give you a sense of this, the sensors on this rod are actually the same, very, very similar, identical in terms of geometry and size to the ones I've just been talking about for the bioreactor and for the hydrogen peroxide generator. And the sensors are here, and the electronics are here. But again, there's so much effort gone into ensuring that we don't get liquid ingression into these sensors. And that's the bit where I've talked about earlier on, NRE, this non-recurring engineering charge. You can see it's very different this week. We often talk about point of care and medical, and we never worry too much about liquid getting into our connections because it's not that type of application. But these are process applications, and they require a lot more engineering. Anyway, the reason I'm showing this picture is because with this, we really have cracked it, because we put these sensors into the soil and we leave them there for 6 months. But it took a lot of engineering to sort of get to that point. So my biggest concern with the bioreactor and the hydrogen peroxide generator is actually ensuring that liquid doesn't get in there. Now, the way I would do it is this, that there's an outlet on here, and essentially I'd potentially make a tube I put Swage Lock in here because I got a suspicion there's some Swage Lock pieces on here. That's just a brand that people use in process engineering quite a bit. And I'd literally just have the sensor going through the wall of the tube. That would have to be, you know, epoxied in. But you have to think about this piece quite a bit because, you know, if the sensor is really robust to the application, then it's permanently in place. But if you find the sensor degrades with time and you have to replace it, then you don't want that. You want this piece to be quite low cost to replace, you know. So there's a sort of engineering challenge and a commercial challenge as well. These are not insurmountable, but, you know, it's hard for us remotely to be able to sort of advise on that at the moment. But I would see that you just put a sensor on the outlet, and it, to be frank, I think it would work fine. You can certainly do a proof of concept quite readily. Now, one of the things that's happening here is, I think, with these more commercial type applications, we've built up this stack of technology where we take the sensor. I know Aftab is online, knows all about this. But we take the sensor. You could say this sensor is either in the flowing stream of hydrogen peroxide, or it's in the earlier photochemical bioreactor, or the photobioreactor. Essentially, we just need a base station, which we have. And what we do is we tend to take the signal from the sensors and send it to a base station. And the base station, via Wi-Fi, would connect to something called Julie. Now, we can have several sensors modules in proximity to one another. So if you've got several bioreactors and they all need monitoring, they can all be monitoring and all sending their data to the base station, and the base station sends the data to the cloud called Julie. And then actually we can then use an API, an application programming interface, to pull the data out of essentially what we're doing and send it across to what you need to do. Because the reason we do all of this is because you can get signal out of sensors, but on occasions, you know, if the flow is chaotic, you can get a lot of noise in the data, and that needs to be smoothed out. If the sensor is, for example, if the plasma generator is going on and off, the baseline or the signal will move around quite a bit. So you have to understand these things, and you have to process the data accordingly. So what we can do is we can put these sensors into the applications. But the electronics will talk to a base station, and the base station will send the data to Julie, and then the data can be pulled out using an API and application programming interface. And I think this is really the future of things. If you're going to do sensors, you really want to have an IoT, an Internet of Things type solution, because it's a better commercial model, to be honest with you, is the simplest way of saying it. So what I want to now do is address question number 3, which is related to question number 1 and question number 2. Question number 1 was about a photobioreactor. Question number 2 was about hydrogen peroxide generation. Question number 3 was really about measuring lactic acid in fermentation broth. So fermentation, for example, is, you know, the process of making alcohol, but you can make other molecules using fermentation as well. I asked a question: is this an R&D effort or is this a commercial effort? Because if it's an R&D effort, that's almost the simplest one. We have a web page, lactic acid sensors on it, or lactic acid sensors on it. There's a couple of videos by Siobhan, and really the lab experiments are not that hard. To watch the videos, not that hard. The commercial one, again, if you're going to measure lactic acid in a bioreactor, then you would really do the same solution that I was talking about earlier on, that the sensors would go into the bioreactor. There'll be a hub which could essentially receive the data, and then we would send the data to the cloud. So that's why I'm sort of asked, is it an R&D or a commercial thing? Because with commercial, I think the world is going in this Internet of Things direction. And so I really wouldn't prescribe or consult that you should do necessarily all the... I understand people want data in the field near the application, but you should always have the intention to send your data to the cloud as well. With lactic acid sensing, you just need a lactic acid sensor, and you just need and a pot. Just drop the sample onto the sensor, and you're essentially good to go. We do have a couple of links to the products here. We do have an application zone where I show how to run the lactic acid sensor, or we show how to run the lactic acid sensor in a different configuration, where you run it in a essentially in a beaker. Again, there's an application zone, and it's under our knowledge base. It's definitely worth watching that. It shows you all lots of different ways of. It sort of shows you that we can run experiments in lots of different configurations, and it's really just choice which configuration you run. This is a bit of a boring slide. It's really a shopping list. There's a lactic acid sensor out there. I recommend generation 1 to get you going. The Anapot, fully functional R&D instrument. Cable, it's very boring. It's a LEMO cable. It has these little crocodile clips, but there's also a connector that you need, and you'll need the 2mm connector, and that's fine. It's an entire shopping list there, and hopefully that really helps. Question number 4. Right, so I'm so sorry. We've talked about measuring pH in a bioreactor. Simple enough. pH sensors exist. pH is the simplest one to do with an Arduino environment. Question number 2 is made simple because hydrogen peroxide is actually generating quite high concentrations. It's complicated because I worry about the lifetime of these sensors in that kind of corrosive environment, and that really has to be sort of checked out a bit. That's interesting. I just had a question coming out. Which topic is going on air? But I wasn't quite sure of the question. Question number 4 is ATP, adenosine triphosphate. So this is just to say that we do have some really intensely good academics working with purine sensors these days. This is a slight side note, but purines are really interesting or indicative of sort of neurological concerns. We became interested because purines are a marker for stroke. I think they're really an indicator of tissue damage, and including tissue damage in the brain. We've just developed a sensor for ATP, adenosine triphosphate, which is, I sort of think it's the energy currency for a lot of, at least for mammalian cells. ATP is a sort of the thing that shuttles energy around our systems, and I've just put it on the website now, or not just, but it's this is a recent development from us, and we have the ATP sensor. If you're into raw signals, we have, it's really good because the gentleman who does this work, or rather him and his team, they do multiple tests, but when you look at their data, you can't always realize that they're actually testing more than one sensor under there. And the reason being is I absolutely insist that they always use our hypervalue electrode, and this is a sort of slightly different matter. What's the world's best screen printed electrode? It's the ZP hypervalue electrode. Why is it the world's best screen printed electrode? Because it's made in really high volumes, and we use it ourselves. So, we actually use our own products to then make other products to put on top of it. So whenever you ask somebody, if somebody is looking for what's called a screen printed electrode, make sure they look for the hypervalue carbon electrodes. It's really reproducible, which means that the guys can then produce really reproducible data. And then when you look at their data, I know it's not, it's essentially non-linear. It's linear in the, we get a very sharp increase, and then it kind of plateaus off. But to be frank with you, signal versus concentration, I was okay with this because I feel like in some clinical applications, it's important to sort of be, whether you're high or low is interesting, but being accurate in the low region is sometimes more interesting. And we can, in the end, I just want to say hi to Ahmet this morning. Hi Ahmet, nice to see you. Ahmet, if anyone's interested, is he's got a cool skill set in electronics and making electronics for biosensors, which is relevant because we have been talking about measuring pH with Arduino this morning. Anyway, we have this ATP sensor. I've put a bit of a link up onto it. This is a direction that we're going with at ZP, and I call this the near future. So indulge me for about 2 minutes. The reason being is at ZP now we have all these sensors, from glucose, oxygen, lactic acid, hydrogen peroxide, pH, down to things now that are sort of, testosterone, troponin, androstenone, ATP, adenosine triphosphate. We've got a lot of sensors. So let's talk about how we're going to deal with all of this. So we have all these sensors, and people can essentially choose a sensor that they're interested in. For example, the purine sensor. The purine sensor then works with our meter. You put it in there, and we have an app. Now, the near future, this is not where we're at today, but then, in fact, we are here today. We can make Bluetooth connection between the app and the meter, and essentially the meter runs, in this case, the purine sensor, gives the data back to the app, and then the app will actually upload it to Julie. But when you've got this whole collection of sensors, we need a new functionality, and this is the near future that we don't have at the moment. But the app, for example, will make a connection to Julie, and in Julie then we'll actually have all the essentially apps or the method files for all the sensors we've got. So if we've got a glucose sensor, there'll be a glucose method file. If we have an oxygen sensor, there'll be an oxygen method file. If there's a lactate sensor, we'll have a lactate. So essentially, you choose the sensor you want, you put the sensor in the meter, you Bluetooth connect the meter and the app, but the app then actually has the capability of pulling upon the Julie app store. The question that so then the app calls upon the Julie app store, and the method file comes down. So this means then that this meter, you can either run it for a glucose sensor, run it for a purine sensor, or an adenosine triphosphate sensor, but we have not enabled this part yet. We have enabled the ability for the app to run the meter to give the data back to the app, and the app to upload it to Julie. But there's a new functionality that we need, that we don't have it, which is actually being able to choose the method file. And so the meter can keep on changing which type of sensor it's actually analyzing. So that's to come, and I mention it because Aftab's here this morning, so he can help me implement it. And then the workflow that we do have already is that these apps run the meters, the data can be uploaded to Julie. In Julie, we can do qualification, make sure the data is good, quantification, make sure the data is turned from raw signal into concentration. And then we can do API, application program interface, where we can actually send that to other people's clouds if they so wish. The reason I was hesitant, there's a question that's come through. I just want to read it. So for capsaicin determination in a sample, can we use screen printed electrodes in Admiral Instruments? So I know Admiral Instruments. I don't know their cyclovoltammetry. But I do know one thing. The gentleman who's asking about measuring capsaicin, which is the molecule in chili, there's another guy online at the moment called Aftab. He runs Technando. So I definitely would have a word with Aftab at Technando regarding that question. Technando's our guy in India. I do know Admiral Instruments. I know they come out of Phoenix, Arizona in the USA, so I am familiar with the company, but I've never run the cyclovoltammetry on their instrument. So in the near future, we're then going to enable these apps to actually call upon the different method files, and so you can essentially use the 1 meter to run all of our sensors, and then upload the data to Julie, and Julie will process the data and send it to whatever cloud system you want via the API. So we're coming up to 1 minute left, so let me just do this. So I clearly recognize that we were asked to measure the dissolved oxygen, the pH, the conductivity, and temperature in a photobioreactor. I limited it just to pH, just to keep it simple in some ways, and just actually get started, because it's a month's worth of work just to get towards pH. The monitoring hydrogen peroxide, I would have no issues in saying, can you measure hydrogen peroxide in that application? I think my concerns would be the corrosion on the sensor, and corrosion is linked to things like duty cycle, how often does this run, and in the end it has to be tried, is the quick answer on it. Lactic acid in fermentation broth, yeah, should work fine. The laboratory setting is something that is done quite often. Doing it in an actual bioreactor, which is similar to question 1 and question 2, that's a lot more engineering effort. And then the biosensor for ATP, really proud of the guys at ZP in Coventry. They developed a new sensor. It looks really quite nice. In order to run it on, for example, the purine meter, we need to implement something in Julie that we haven't yet implemented, but that is something that we intend to implement. So thank you very much. As I say, if you've got any questions regarding Admiral Instruments and you're located in India, there's a company called Technando. Aftab runs it. They're online at the moment, and I'd give them a quick shout. So thank you very much. As always, any questions, send them through to us, and we will answer them as we do in this webinar. Okay. Thank you very much, guys. Take care. Thank you for the question on capsaicin and Admiral Instruments. Thank you to Aftab for being here this morning. Also to Armet. Just a quick shout out to Armet. If anyone finds him on LinkedIn, he's got a good background in electronics for biosensors.